Electronic structure of the atom. At this point, we need to see how the information given above is used to develop the complete picture of an atom. The underlying principle of how the electrons are arranged is based on the energy of each orbital. Electrons will fill the orbitals that have the lowest energy first, much as water always flows downhill. While the numerical values of the energies of the orbitals are not important here, the order from lowest to highest energy is important. That sequence is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d. This sequence is known as the Aufbau, spelled AUFBAU, or energy order. It need not be memorized since it may be quickly obtained from the structure of the periodic table. Figure 1.10 shows the long form of the periodic table divided into shaded blocks labeled S, P, D, and F for the highest energy electron in each atom. Figure 1.10, expanded periodic table divided to show the regions where S, P, D, and F electrons are the highest energy electrons in each atom. Reading across this periodic table, we can see that the energy ordering is an integral part of this table. The first period represents the 1s electrons. Filling the second period adds the 2s electrons on the left and then the 2p electrons on the right. The third period fills with 3s and then 3p electrons, the fourth period with 4s, 3d, and 4p electrons, and the fifth with 5s, 4d, and 5p electrons. Notice that in the fourth and fifth periods, a d electron has a number that is one less than the period it is in. The sixth period fills with 6s, 4f, 5d, and 6p electrons, and the seventh with 7s, 5f, and 6d electrons. Once again, notice that the d electrons have numbers that are one less than the period number. In addition, the f orbitals have numbers that are two less than the period number. Electronic configurations. Once the energy order of the orbitals is known, the electrons in any atom may be described as the electronic configuration. Chemists use two forms of this configuration to display information. The first is the complete electronic configuration, which lists all of the electrons in the atom. The second is an abbreviated version that groups all of the inner electrons together and lists only the highest energy electrons. Complete electronic configurations, NL-ESH. In complete electronic configurations, the electrons present are listed by designating the principal energy level, represented by N as a number, the sublevel, represented by L as a letter, and the number of electrons represented by X in each sublevel is also included. Atoms are built up by adding electrons to the lowest energy sublevel possible. To obtain an electronic configuration for an element, the number of electrons is determined from the element's atomic number. Then, these electrons are placed into the sublevels, completely filling one sublevel before starting to fill the next one. Several examples are shown in Table 1.5. Table 1.5, Electronic configurations of selected elements. The table lists several elements along with their complete electronic configurations. For sodium, which has the chemical symbol Na, the complete electronic configuration is 1s2, 2s2, 2p6, 3s1. For antimony, which has the chemical symbol B, the complete electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, d10, 5p3. For cobalt, which has the chemical symbols Co, the complete electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. For chlorine, which has the chemical symbol Cl, the complete electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Important exceptions to Aufbau ordering. The above examples follow the Aufbau order in the filling of the sublevels. Many elements, however, do not follow the Aufbau ordering, as shown in the table of electronic configurations in Appendix 1. The only exceptions to the Aufbau ordering that are important at this time occur in the electron configurations for chromium, molybdenum, copper, silver, and gold. These are listed in Table 1.6. It is apparent that the completely filled D sublevel of copper, silver, and gold confers stability to the atom at the expense of unfilling the previous S sublevel. For chromium and molybdenum, it appears that a half-filled D sublevel also confers stability, once again at the expense of a previously filled S sublevel. AP students do not need to memorize exceptions, but do need to be able to explain them. 1.6 Electronic configurations of selected elements. For copper, SU, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. For silver, Ag, the electronic configuration is 1s2, 2s2, 2ps2, 3p6, 4s2, 3d10, 4p6, 5s1, 4d10. For chromium, Cr, the electronic configuration is 1s2, 2s2, 2p6, 3p6, 4s1, 3d5. For molybdenum, Mo, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, 4d5. Abbreviated electronic configurations. When atoms react with each other, their first point of contact is the outermost highest energy electrons of each atom involved. In fact, the inner core of lower energy electrons and the nucleus play virtually no role in most chemical reactions. These inner electrons may be represented by the noble gas at the end of the period, just before the period containing the element of interest. In a complete electronic configuration, all the electrons up to the last completely filled p6 sublevel are the inner or core electrons. They may be replaced by the symbol in brackets for the appropriate noble gas. For iron, the complete and abbreviated electronic configurations are as follows. Argon equals 1s squared, 2s squared, 2p6, 3s squared, 3p6. Iron equals 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, 3d6. Iron equals argon, 4s squared, 3d6. Notice that the last completely filled p orbital is the 3p, and that argon has the electronic configuration of all of the electrons up to and including the 3p6 electrons. Valence electrons, in many instances, chemists are interested in the outermost electrons in an atom. These are the valence electrons. In a practical sense, these include only s and p electrons of the atom. For any given atom, the principal energy level of the outer d electrons is always one less than the principal energy level of the s and p electrons. Similarly, for the f electrons, the principal energy level is always 2 less than the outer s and p electrons. How to count valence electrons. Determining the number of valence electrons for any atom involves counting the group's columns from the left of the periodic table to the element of interest. The d and f electrons shown in figure 1.10 are not counted. Valence electrons are often shown as dots surrounding the symbol of an atom, as shown in figure 1.11. Figure 1.11, representation of valence electrons as dots around the atomic symbol for the first 3 periods in the periodic table. Tip: only s or p electrons count as valence electrons. You may often see the electrons unpaired in groups 2a, 3a, and 4a. Hund's rule. Notice that the second valence electron, second column in figure 1.11, is represented as a pair rather than placing them on opposite sides of the symbol. This is done to indicate that the electrons are paired in the completed s orbital. The third through eighth columns fill the p orbitals. Hund's rule requires that p, d, or f orbitals in a sublevel must all be filled with 1 electron each before a second electron is allowed to pair in any orbital. The 3 separate p orbitals fill with 1 electron each in boron, carbon, and nitrogen, as shown by the unpaired dots in figure 1.11. The electrons for oxygen, fluorine, and neon then form pairs until all of the p orbitals are filled. Electrons begin to pair up only if every orbital in the sublevel is first occupied with 1 electron. Orbital diagrams. Electronic configurations and valence electrons are useful for most purposes in describing the structure of the atom. However, since all of the different orbitals in a sublevels are lumped together and some detail is lost. To see that detail, orbital diagrams which show each of the orbitals in the valence shell of the atom as a box or circle are often used. Arrows representing electrons are placed in each orbital. The second electron in each orbital has the arrow facing in the opposite direction from the first, indicating that their spins are paired. Figure 1.12 shows the 3 possible situations for an orbital. Figure 1.12, orbital boxes that represent an empty orbital, an unpaired electron, and a pair of electrons, respectively. Orbital diagrams are used mainly to describe the valence electrons, since all of the inner electrons will be paired. At times, the d electrons are also shown in these diagrams. The orbital diagrams of the first 10 elements are shown in Figure 1.13. The electrons are added to each sublevel, starting with the 1st sublevel. The arrow pointing upward traditionally represents the first electron in each orbital until each orbital in a sublevel contains 1 electron. Then the downward arrows, representing electrons of opposite spin, are added to complete the sublevel before a new sublevel starts to fill. Let Figure 1.13. Orbital diagrams for the first 10 elements, showing only the valence electrons. In later chapters, we will want to show energy differences between the orbitals along with the orbital diagrams. This can be done by drawing the orbitals as shown in Figure 1.14 to indicate that the 2p orbitals are higher in energy than the 2s orbitals. Figure 1.14, orbital diagram showing that the 2s electrons in carbon have a lower energy than the 2p electrons. Quantum numbers. Erwin Schrödinger developed the wave equations describing the probabilities of where the electrons are located in the atom. As mentioned earlier, these equations require 3 integers, called quantum numbers, which describe each electron. The quantum numbers have definite rules for their possible values. The principal quantum number, n, may have any integer value starting from 1. This represents the principal energy level of the atom in which the electron is located and is related to the average distance of the electron from the nucleus. 2. The azimuthal quantum number, L, may have any number from 0 up to 1 less than the current value of n. L equals 0 n minus 1. This designates the sublevel of the electron and also represents the shape of the orbitals in the sublevel. 3. The magnetic quantum number, ml, may be any integer, including 0 from negative L to positive L. ml equals negative L 0 positive L. This quantum number designates the orientation of an orbital in space. These orientations are shown in Figures 1.7 through 1.9. 4. The spin quantum number, ms, may be either positive 1/2 or negative 1/2. This represents the spin of an electron. For electrons to pair up within an orbital, one electron must have a value of positive 1/2 and the other a value of negative 1/2. This quantum number is not needed for the wave equations, but it is required to satisfy the Pauli exclusion principle described below. The final requirement, known as the Pauli exclusion principle, is that no 2 electrons in the same atom may have the same 4 quantum numbers. The AP guide clearly states that students will not be asked to assign a specific set of quantum numbers to an electron in an atom. This is very reasonable because a question like that has many correct answers and therefore cannot be part of a multiple choice question. It is also too complex for free response questions. However, if you are an AP student, a teacher, or a tutor of AP chemistry, you will be using quantum numbers. Recall that the 4 quantum numbers are n, L, ml, and ms. You will be asked to write, construct, or explain electron configurations of elements and ions using the first 2 quantum numbers n and L. These are shown in tables 1.5 and 1.6. They tell us the distance from the nucleus and the shape of the orbitals. If you discuss the shapes and orientations of orbitals, e.g. the 3 different p orbitals that point in the x, y, and z directions, and the more complex d orbitals shown in Figures 1.8 and 1.9, then you're talking about the L and ml quantum numbers. Finally, if you explain electrons have a spin of positive 1/2 or negative 1/2, and that each filled orbital must have a pair of electrons, each with opposite spins, then you have just used the ms quantum number. The message is this: the AP chemistry exam tests you about the uses of quantum numbers extensively. Exercise 1.1. Designate each of the following sets of quantum numbers as possible or impossible according to the above rules. A. Principal quantum number 1, azimuthal quantum number 0, magnetic quantum number 0, spin quantum number positive 1/2. B. Principal quantum number 1, azimuthal quantum number 3, magnetic quantum number 0, spin quantum number positive 1/2. C. Principal quantum number 3, azimuthal quantum number 2, magnetic quantum number 0, spin quantum number positive 1/2. D. Principal quantum number 2, azimuthal quantum number 2, magnetic quantum number 2, spin quantum number negative 1/2. E. Principal quantum number 3, azimuthal quantum number 2, magnetic quantum number 2, spin quantum number negative 1/2. F. Principal quantum number 3, azimuthal quantum number 1, magnetic quantum number negative 1, spin quantum number positive 1/2. G, principal quantum number 4, azimuthal quantum number 2, magnetic quantum number -2, spin quantum number -12. H, principal quantum number 4, azimuthal quantum number 4, magnetic quantum number 0, spin quantum number +12. I, principal quantum number 3, azimuthal quantum number 2, magnetic quantum number 1, spin quantum number 0. J, principal quantum number 1, azimuthal quantum number 1, magnetic quantum number 1, spin quantum number +12. K, principal quantum number 6, azimuthal quantum number 4, magnetic quantum number -4, spin quantum number -12. L, principal quantum number 5, azimuthal quantum number 3, magnetic quantum number -2, spin quantum number +12. M, principal quantum number 2, azimuthal quantum number 0, magnetic quantum number 1, spin quantum number -12. Principal quantum number 5, azimuthal quantum number 0, magnetic quantum number 0, spin quantum number +12. O, principal quantum number 3, azimuthal quantum number 1, magnetic quantum number 2, spin quantum number -12. A, C, E, F, G, L, and N are valid. The others violate one or more quantum number rules shown above as follows. B, D, H, and J break Rule 2. M and O break Rule 3. I breaks Rule 4, hashed significance of the quantum numbers. The 4 quantum numbers might seem like just data to memorize with their rules, but it's key to understand that these numbers represent real physical properties of the atom. Here's a simplified overview. 1. Principal quantum number, N, describes the average distance of the electron from the nucleus or the size of the energy level. 2. Azimuthal quantum number, L, represents the shape of the orbitals within the sublevel, as shown in figures 1.7, 1.8, and 1.9. 3. Magnetic quantum number, mil, indicates the orientation of each orbital in space. 4. Spin quantum number describes the spin of the electron.